today we'll be learning about periodic trends in atomic radius. So let's look at this term trend or trends. What it means is that on the periodic table there are very specific properties which are repeated again and again, and we'll be looking at atomic size today or atomic radius. So when we look at atomic size, our first problem is where do we start measuring an atom? Okay, and we know that around the nucleus we have electron cloud. So it's very hard for us to measure the electron cloud because it does not have a definite edge. So, how do we get around this problem? Well, we measure more than one atom at a time. So, let's look at this diagram here. This is a diatomic molecule, and this would be atom 1, and this would be atom 2. So, atomic radius would be half the distance between the two nuclei of atoms. So, the distance from here to here, this is half the distance. Now it's easier for us to measure the size of an atom. And sometimes atoms can be measured in a solid state by X-ray diffraction method also. So there are different ways we can measure atomic size. There are three factors that affect the size of an atom, and we'll be looking at all three of them one by one. We'll start with the first one, which is energy level. And higher energy level is further away from the nucleus. So let's see, what do we mean by this? Let's compare two different atoms. We'll compare hydrogen and lithium. They both are in group 1, and hydrogen has electron configuration of 1s1 and lithium has electron configuration of 1s2, 2s1. So if we were to draw the Bohr diagram, this is how we'll draw. That's the nucleus. This is the first energy level. And lithium, that's the nucleus. This is the first energy level. And then we have the second energy level. Okay. And now let's draw the electrons. Hydrogen has 1 electron there, and lithium has 3 electrons, 2 electrons in the first energy level, and then the third electron in the second energy level. Okay, so let's compare the size of hydrogen to lithium. Since lithium has more energy levels, we can now say by looking at this diagram that lithium is bigger in size as compared to hydrogen. And that's what it means. Higher energy level is further away from the nucleus. Higher energy levels would mean that the size of an atom is much bigger than other atoms if we are comparing them like this, hydrogen to lithium. Okay, so let's look at the second one, which is the charge on the nucleus, which is also known as Z effective or effective nuclear charge. We know that inside nucleus we have protons and neutrons. And neutrons are neutral in charge, protons are positively charged. So the charge on the nucleus would be because of the protons. More the number of more protons, more would be the charge on the nucleus. Let's compare two different elements. We'll start with hydrogen and helium. Hydrogen has 1 electron in the first energy level. Helium has 2 electrons in the first energy level, 1s2. So let's draw the Bohr diagram. We have the nucleus here, and then we have 1 energy level. For helium also we have the nucleus and we have an energy level there. Okay, let's draw the electrons now. We have only 1 electron and we have 2 electrons here. Okay, let's represent the charge here on the nucleus. Hydrogen has only one proton, so I can say now that the charge on the nucleus is +1, and helium has two protons, and the charge on the nucleus is +2. So helium has a higher charge as compared to hydrogen in the nucleus because of the difference in the number of protons in the nucleus. So let's compare the size of this atom to the size of this atom. So what's happening here is both hydrogen and helium have electrons in the first energy level. And the only difference between them is that the charge of the nucleus is higher for helium as compared to hydrogen. So the pull of the nucleus on its electrons is going to be more here as compared to hydrogen. So uh, the, the size of helium is going to be smaller as compared to hydrogen. Okay, so more positive charge would mean that there's more pull in the electrons. And remember, in this example, we are comparing helium, helium to hydrogen, and both of them are in period 1. Okay, okay. So let's start with the third factor that influences atomic size, and that would be the shielding effect. So let's discuss about the shielding effect. Okay, shielding effect. Hey, before we can discuss this, let's discuss two vocabulary words. The first one is known as core electrons, and the second one is valence electrons. And we know what valence electrons are. Valence electrons are the electrons that are present in the outermost energy level. And the core electrons are the electrons that are present in inner energy levels. Okay, so let's look at, mm, let's say, lithium. Lithium has 1s2, 2s1. The valence electrons are these, and the core electrons would be these. 1s2, the electrons present in the first energy level would be the core electrons, and the electrons present in the second energy level would be the valence electrons. So now let's look at another example. And we can look at aluminum, which has 13 electrons in it. The electron configuration for aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. Okay, so the valence electrons for aluminum would be these, and the core electrons for aluminum would be these here. The electrons that are present in the inner energy levels. Okay, so the electrons in the first energy level and the second energy level would be the core electrons for aluminum, and the electrons that are present in the third energy level would be the valence electrons for aluminum. Okay, now shielding effect means the inner electrons, which are the core electrons, they act as a shield to the outer electrons from the nucleus, and therefore would decrease the pull of the nucleus on its valence electrons. So let's take an example of lithium. And we know that lithium has two energy levels. Okay, so the electrons that are present in the first energy level, let's draw the electrons. Okay, so these two electrons would shield the pull of the nucleus on this electron on the second energy level. So that is the shielding effect. More the core electrons, more would be the shielding effect, and less would be the pull of the nucleus to on its valence electrons. Okay, so let's take aluminum as our example, and we are going to draw the Bohr model for aluminum. That's the first energy level, second energy level, and then we have the third energy level. And I'm going to put the electrons now. There are two electrons here, and there are 1, 2, 3, 4, 5, 6, 7, and 8. And in the third energy level, we have 1, 2, and only 3 electrons. Okay, so the electrons that are present in the first energy level, which is this, and the second energy level, which is this, would be the core electrons, and they act as a shield, like a shield between the nucleus and its valence electrons. So they are acting as a shield between the nucleus and the valence electrons, so reducing the pull of the nucleus on its valence electrons, or the hold of the nucleus on its valence electrons. More the core electrons, more would be the shielding effect. Okay, and less would be the hold of the nucleus on its valence electrons. Okay, so those are the three factors that affect the size of an atom: energy level, the charge on the nucleus, and the shielding effect. Okay, so let's look at this shielding effect again. So the electrons on the outermost energy level has to look through all the other energy levels to see the nucleus. So the second electron has the same shielding if it is in the same period. Okay, and the shielding increases as we move down a group and is constant across a period. So let's look at this one a little bit more in detail. So what do we mean by down a group? So let's look at group 1, and we start with the hydrogen, lithium, sodium, and potassium. Okay, and a hydrogen electron configuration is 1s1, lithium is 1s2, 2s1, sodium is 1s2, 2s2, 2p6, and 3s1, and potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. So as we move down the group, we see that the energy levels are increasing, and so is the number of core electrons. The core electrons are also increasing as we move down the group. And that's what it means. The shielding effect increases as we move down the group. So the hold of the nucleus on its valence electrons is decreasing as we move down the group, and the size of an atom is increasing as we move down the group. Okay? Now let's look at the second point here, which says that across a period, the shielding effect is constant. So what do we mean by being constant? And we're going to start with uh, lithium, beryllium, boron, and carbon. And all of these elements are in period 2. Lithium has this electron configuration. Beryllium has this electron configuration. And boron has this 1s2, 2s2, 2p1. And carbon is 1s2, 2s2, and 2p2. So the number of core electrons across a period are staying constant. So let's look at these core electrons. Electrons that are present in the inner energy levels. And we have 2 electrons in lithium as a core electrons. And let's look at beryllium now. There are only 2 electrons which are the core electrons. Boron electrons, there are only 2 of them as core electrons. Again, only 2 electrons as core electrons. So that's what we mean, that the shielding effect is constant across the period. Since the core electrons are same, there is no change in the shielding effect across the period. It remains constant. Okay, so the shielding effect across a period is constant, but the effective nuclear charge is increasing. Now let's look at the charge on the nucleus. Okay, lithium has +1 charge, +3 charge. Beryllium has +4 charge. Boron has +5, that means 5 protons in the nucleus, and carbon has 6 protons in the nucleus. So as we move across this period, we see that the charge on the nucleus is increasing. Okay, the hold of the nucleus on its electrons is increasing, and the shielding effect is constant. Okay, so that's what it means. Okay, so let's combine everything that we have learned so far. Okay, again, you see a diagram here of group 1 elements, and we have hydrogen, lithium, sodium, potassium, and rubidium. And you can see that the size of an atom is increasing as we move down a group. Okay, the size of an atom is increasing as we move down a group. Now, why is the size increasing? Well, we know that the energy level is increasing. So there are 3 factors. Again, remember, atomic size depends on 3 factors. Energy level is increasing, right? Okay, yes, the number of protons in the nucleus are increasing, but energy level plays a much stronger role in the size as compared to the nuclear charge as we move down a group. And also the shielding effect is increasing. The shielding effect is increasing. That means the hold of the nucleus on its valence electrons is decreasing, and this is allowing the size to increase. Okay, so the increased size of the energy level down the group outweighs the increase in the nuclear charge. So the trend is that as we move down the group, the size of an atom is increasing or increases. Okay, so what happens as we move across a period? So what happens to the size of an atom? So let's look at this diagram here. This is period three. So we start with sodium and we have magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. As we move across, that's the terminology that we will be using. As we move across or as we go across a period, the radius gets smaller, and we can see that in this diagram. Now, why is it that the radius is getting smaller? The reason is that electrons are in the same energy level. Electrons are added in the same energy level as we move across the period. The nuclear charge is increasing across the period. The number of protons are increasing. Electrons are added in the same energy level, and the shielding effect is constant. And because of that, the hold of the nucleus on its outer electrons is increasing as we move across the period. And since the hold of the nucleus is increasing, it's able to pull its electrons closer to itself. So the nucleus is able to pull its electrons closer to itself and shrinking the size of an atom. Okay, so there are again three reasons that help us with defining the size. The first one is energy level. The second one is size, the nuclear charge, nuclear charge. And the third one is the shielding effect. So all three things together would be able to help us with the periodic trend in atomic size. Let's summarize what we learned up till now. As we move across a period, the atomic radius decreases, and as we move down a group, the atomic radius increases. So that's the trend that we see on the periodic table. There's a small correction that we have to make on this diagram is that hydrogen is around 50 picometers. So picometers. So the radius here, everything is in picometers, and this is around 31 picometers. Okay, PM is picometers. Okay, the size of an atom can be measured in picometers or nanometers. Mostly you'll see it as picometers. Okay, so this summarizes our trend, our periodic trend for atomic